Hello, everyone. Welcome to a new lecture of our course on heterogeneous systems. Today, we are going to continue talking about parallel patterns, and in particular, we are going to talk about how to compute with sparse matrices on GPUs. Remember that in previous lectures, we have covered other important parallel patterns. The first one of them was the reduction operation, which is an operation that reduces a set of values to a single value. It requires an operator that is associative, commutative, and has an identity value. And this is one of the key primitives in parallel computing. For an optimized high performance reduction on GPU, we have to be very careful about intra-warp divergence, and we have to map data to threads or threads to data in a way that we minimize warp divergence, and this way we maximize the warp utilization. The second parallel pattern that we covered in this course was histogram computation. In this case, we can, by using histograms, reduce the dimensionality and extract notable features of large data sets. In a histogram, what we do in histogram calculation, what we do is counting what's the number of occurrences of each possible value. And when we are doing this in parallel, it might turn out that two threads that are concurrently running need to update the same bin of the histogram at the same time. In order to avoid data races, we'll have to use atomic operations. And as you know, atomic operations entail some overhead because in these cases, they serialize the execution, but we discussed some techniques to optimize this. For example, the privatization, creating local subhistograms and then merging them. Another important pattern that we cover is convolution. Convolution applies a filter or a mask on each element of the input value of the input data set and calculates a weighted sum of the neighboring input elements. Here you can see how to do it for one-dimensional data structures, here for two-dimensional data structures, for example, images. This is the kind of convolution that is used in convolutional neural networks. And we also discussed in the lecture how to lower the convolutional layer to a matrix multiplication that can even fit better the hardware of the GPU. More recently, we talk about another key primitive is prefix sum, an operation that takes an input array and an associative operator and returns an output array that is the result of recursively applying the associative operator on the elements of the input array. Remember as well that we discussed different ways of optimizing, implementing a scan and optimizing it. All these versions were hierarchical, meaning that we operate in different steps and at different levels of the software hierarchy. For example, in this slide, you can see a scan, add version when we first start performing a per block scan. Then we do a scan of partial sums, and finally we add the partial sums to the corresponding chunks previously scanned by each of the blocks. We also discussed like the low-level algorithms. We presented Brent-Kohn and also this Cogistone that is likely more suitable for GPUs. We discussed as well how to optimize the implementation of these algorithms. So now let's talk about sparse matrices and sparse matrix computation. For everyone to be on the same page, let's first distinguish between a sparse matrix and a dense matrix. A dense matrix is a matrix where the majority of elements are not zero. A sparse matrix is a matrix where the majority of elements are zero. And most matrices in the real world are sparse. This presents or provides us with some opportunities because we don't need to allocate the space for zeros, so we can save memory capacity. We don't need to load zeros. We don't need to access them from memory. In principle, they are useless, so we can save memory bandwidth. And finally, we don't need to compute with zeros because if it's an addition, the result will be the same as the other summand. If it's a multiplication, the result will be zero. So by knowing that, we can also save computation time. And as I said, sparse matrices are widely used. They are widespread today. We can find them in recommender systems. We can find them in graph analytics or in neural networks. And real-world matrices are highly sparse. This is an example from Facebook or from YouTube. By looking at this, we are sure that we need to find sparse matrix compression formats that are efficient and provide and allow us to have efficient storage and computation as well. So let's discuss how to compress matrices with different storage formats, and then also how to compute by using these storage formats. So regarding the sparse matrix storage formats, there are many different ones, but some of the most popular ones are the coordinate format or ZOO, the compressed sparse row CSR, the LPAC format ELL, and the jagged diagonal storage JDS. There are many more. These are the ones that we are going to talk about, at least in the beginning, and later we will present another ways of optimizing the space, optimizing the indexing, and in the end, optimizing operations and algorithms with sparse or using sparse matrices. When choosing the right storage format or compressed format for the matrices that you want to handle, it's important to take into account several design considerations. First of all, space efficiency that relates to the amount of memory that is consumed. Second, flexibility that relates to the ease of adding or reordering elements. Accessibility, the ease of finding the desired data, the memory access pattern, whether it enables coalescing and GPUs or not, and also load balancing. In the end, trying to minimize control divergence. We are going to use SPMB as the key primitive to explain how we operate using these compressed matrix formats. The choice of the best format depends on the computation, on the specific algorithm, and also matrix characteristics. For example, the sparsity. As I said, we are going to use sparse matrix vector multiplication as the key primitive that we are going to see how to implement with different storage formats on the GPU. In sparse matrix multiplication, the operation that we essentially perform is the dot product of each row of the sparse matrix and the vector itself. So in order to compute this element here, we calculate the dot product of this row and the vector. In order to calculate this element of the output here, we perform the dot product operation of this row and the input vector. So let's start with the coordinate format. This is the original matrix, and this is how we represent the compressed matrix. Observe that what we are doing is store every non-zero element along with its own with its row index and column index. For example, this element here has a value 1 and it's located in row 0 and column 0. This element here, its value is 7 and it's located in row 0, column 1. So how do we implement SPMB using the COO format? One thing that we can do here is to, in this parallelization approach, is assign one thread per non-zero element. As you can see, so we would be assigning one thread to each of the non-zero elements in the matrix. Because we are using the compressed representation, we have consecutive threads accessing consecutive elements, their values and their exact location, row and column. Good thing here is that the memory accesses are going to be coalesced. However, one key drawback of this implementation is that we will have multiple threads writing to the same output, and this will require to use atomic operations. To calculate this element here, we have these two threads. So these two threads need to perform matrix, we need to perform multiplication of the corresponding element to the corresponding element of the input vector and finally accumulate in the same location. And to do so, we need to use atomic operations. And we already know what are the problems with atomic operations because they serialize the execution. Well, this is the sample code for this SPMB using the COO format. As you can see, we access the matrix for each individual thread. We access the matrix in order to obtain the row and the column of the particular value that we are going to use. Then we read the value, and then we, after multiplying by the corresponding element of the input vector, we accumulate using an atomic operation. So Atomic operations are pretty costly, or might be pretty costly because of serialization, where we have especially threads of the same warp trying to update the same memory locations. But we have discussed different ways of optimizing for atomic operations. And one of the ways that we could potentially use here are the coalesced atomic operations that we explained in the lecture corresponding to histogram calculation. And here you can see the slide just to remind how to implement these coalesced atomic operations. So COO has trade-offs and has advantages and disadvantages. Regarding the advantages, it's flexible because it's easy to add new elements to the matrix, and non-zeros can be stored in any order because every non-zero is identified by its row and column. In terms of accessibility, given a non-zero, it's easy to find the row and the column, and it guarantees coalesced memory accesses and no control divergence, because each thread is performing the same amount of computation, reading elements from the matrix, reading elements from the vector, performing multiplication, and then using the atomic operation. There is serialization, but no control divergence in principle. Disadvantages: accessibility. Given a row or a column, it's hard to find all non-zero elements. We will need to search, we will need to scan the whole adjacency matrix in order to find these, the compressed adjacency matrix, in order to find these elements. And we have to use atomic operations, as we already said. So the next format that we are going to discuss is compressed sparse row, or CSR, that is widely used, probably is the most popular format, and provides high compression ratio. It's also used in very multiple state-of-the-art libraries and frameworks like Intel NKL, Library Taco, Ligra, Polymer, GANROC for GPUs, etc. So in this compressed sparse row, observe that what we do is storing the non-zeros of the row adjacently and an index to the first element of each row. So now for each non-zero value, we are storing the column index, and then we have one single pointer per row. So as you see, these two first elements, 1 and 7, start here at pointer 0, but then the next elements, the elements corresponding to row 1, start here at element at pointer this index 2 of the array of columns, of the arrays of columns and values. And this is the way that we store the matrix in the CSR format. How do we perform computation of SPMB using the CSR format? In this parallelization approach, what we are going to do is assigning one thread to the to loop over each input row sequentially and update the corresponding output element. So this is how we assign the rows to the different threads that participate in the computation. If we look at how we do it in here with the compressed format, in the first iteration, every thread accesses the first element of the row. They really know where to go because they first check this row pointers array, and then they start iterating. They go element by element of the row. They go to the corresponding element, or they read the corresponding element of the vector, perform the multiplication, and then accumulation. And here you can see how the code looks. First of all, we have to loop over the elements that belong to one row. That's why we are using here as for the index of the for loop, the array of row pointers. Then we read every column index, we read every value, we find the corresponding element of the vector, perform the multiplication and accumulation. And as you see here, we don't need to use atomic operations because now every thread is working on a different row of the matrix and then also working on a different element of the output vector. So trade-offs of CSR versus COO in terms of advantages. There is more space efficiency because row pointers are smaller than row indices. We just need to keep one pointer per row. In terms of accessibility, given a row is easy to find all non-zero elements, It's possible to avoid atomic operations, as I mentioned before. And in terms of these disadvantages, in terms of flexibility, it's hard to add new elements to the matrix. In terms of accessibility, given non-zero, it's hard to find row. Given a column, it's hard to find all non-zeros. And the one big issue here is that the memory accesses are not coalesced, because every thread is accessing at a certain distance from the neighboring threads, because they access values of the same row. And also there is control divergence, because the number of non-zero elements that we may have in each row might be very different, and this will make that some threads finish the execution earlier than others. So we have control divergence and we have load imbalance. Sorry. Another important and useful compressed matrix format is the compressed sparse column. It's essentially the same, or CSC. It's essentially the same as CSR, but in this case, we group the non-zeros by column. And instead of having an array of pointers to the beginning of the rows, we have an array of pointers to the beginning of the column. So as you can see how we store here 1 and 5, 1 and 5, that are the non-zero elements of this first column, then 7, 2, 7, 2, and we store the corresponding row, and we use, in order to access row and values, we use these column pointers. The next format is the LPAC format, or ELL. This is the matrix that we are compressing in this case. Now we are going to do something similar to CSR. We start doing something similar to CSR, which is compressing by row. So we place next to each other all those non-zero values that belong to the same row. We keep the value of the column, and we keep with the index of the column, and we keep the value. And then what we do is pad in the rows so that they all have the same size. As you see, these are padded positions. All of these are, in reality, they just have useless values, but this is going to enable us to achieve better accesses, better performance with this sparse matrix representation. So now, next thing that we do is storing in column major order. So that means that the way that we are going to lay out this matrix, or this array of column indices and this array of non-zero values is in column major order, as you see. And this is how it's going to look in memory. So now, how do we perform the multiplication? How do we perform the SPMB calculation? So in our parallelization approach, we assign one thread to loop over each input row sequentially and update the corresponding output element. So now the good thing is, because of the way that we have laid out and stored in memory in column major order, now we have that threads accessing, in this case, the first element, the first non-zero value of each row. They are accessing these values in adjacent memory locations. So these result in coalesced memory accesses. When we continue the execution, the later iterations, still we have coalesced memory accesses until the end. The only issue that we may have here is that at some point, some of the threads won't do useful work, because in reality they have reached the end of the row and they are just accessing padded elements. And this is how the code looks. Observe that we have these for loop here to iterate over all the elements of a row. And these, so when we calculate the index for each successive element of the matrix, we need to use this parameter here that gives us the number of rows of the matrix, because that's the distance of the consecutive elements, of consecutive iterations for each of the threads that execute these for loop. Then we access column, we access the non-zero element, we perform the multiplication, and we perform the final accumulation. So what are the trade-offs of this ELL format? Advantages: it's flexible in the sense that we can add new elements as long as one row is not full, we just need to replace one of the padded positions with the actual value that we want to store. In terms of accessibility, given a row is easy to find all non-zeros, given a non-zero is easy to find row and column. The memory accesses are coalesced for SPMB, as we have just seen. And in terms of disadvantages, it's not so much space efficient because this overhead due to padding. In terms of accessibility, given a column, is hard to find all non-zeros, and also it has control divergence because, as you have seen, not all threads have to compute the same on the same amount of elements because there is not the same amount of non-zero elements in each row. So there is a hybrid format that mixes ELL and COO in order to try to improve the features, the characteristics of ELL by taking advantage of some characteristics of COO. So remember that in ELL for our matrix, what we do is in this ELL format is we keep column and value, we pad each of the rows, and what we propose in this hybrid format is to keep all values, to keep all rows relatively short, and only for those rows that are very long ones, we use a different format. We use COO, as you can see. So in this case, we have decided that the length of each row is only 2. And for those 2 rows here, the green one and the pink one that are longer than 2, what we are doing is storing in the COO format the remaining elements. There are trade-offs here, of course, similar to ELL. We have the so this format is similar to ELL, and it has the added benefits from using COO. It's more space efficient because we have less padding, because we don't have to pad until the size of the longest row. We can just fix to do it, for example, row size equal 2, as in the previous example. It's flexible in the sense that we can add new elements to any row. If one row is already full, then we can start using the COO format for the new elements of the row, and there is also less control divergence. We can have all threads performing more or less the same amount of computation while they are using the ELL part of the format. When they have to go to the longer rows, to the COO part of the format, we can have multiple threads working there, or we can even have the CPU operating on those very long rows. The next format that we are going to discuss is this JDS, diagonal storage. As you see, this is our input matrix. And again, we are going to group non-zeros by row, same as we did with CSR. But after doing that, we are going to row by size. And remember, what's the original row index? So we see that this is the longest row. So this longest row is going to be on top of this structure of column index and non-zero values, but we also have to store what was the original row index. This is row 1 in the original matrix. And then we store the non-zeros in column major format, as we did also in ELL. So this is how the column array and the values array is going to look in memory. And we also need to remember where the non-zeros of each iteration start. So essentially, this iteration pointer is going to tell the threads where do they have to start looking at when they are performing the successive iteration. So for the participating threads in the very first iteration, they will start here, and then depending on what's their thread index, they will go to the specific element here in the value and column array. In the next iteration, it's index, so iteration pointer is 6 in this case, so they will start the second iteration from this element. So let's see how we execute or how we implement the SPMB operation with the JDS compressed format. We assign one thread to loop over each input row sequentially and update the corresponding output elements, same as we did with other matrix formats. Observe that here the memory accesses are coalesced as well, and it keep being coalesced until the end, and only at the very end some threads start dropping out, the same threads start being idle. But in all this process, we are minimizing control divergence, because observe that all threads are working almost until the end, are working, are active almost until the end of the execution, until the final iterations. And a good thing here is that minimize control divergence and we increase load balance. So trade-offs. Advantages, it's space efficient because there is no padding in this case. It's accessible in the sense that given a row, it's easy to find all non-zeros, and the memory accesses are coalesced, and we minimize control divergence as we discussed. In terms of disadvantages, in terms of flexibility, it's hard to add new elements to the matrix. In terms of accessibility, given a non-zero, it's hard to find a row. Given a column, it's hard to find all non-zeros. So we have seen that all these matrix formats have pros and cons, so that's why it makes sense to ask ourselves whether it's possible to design a better compression format. And that's something that we tried in past work with some interesting results. One of the reasons for trying that is not only trying to increase the space efficiency and save memory capacity, but also trying to reduce the indexing overhead in sparse kernels. And indexing overhead essentially means to find the actual values of the matrix and the vector. So in the case of SPMB, for example, in SPMB, we have to index for every non-zero element of the sparse matrix to multiply with the corresponding element of the vector. In another sparse matrix computation, like the sparse matrix multiplication, we need to do index matching for every inner product between the two sparse matrices. And so indexing is expensive for most sparse matrix kernels. And we have actually some motivation results showing this. This is for a sparse matrix addition, a sparse matrix vector multiplication, and sparse matrix multiplication. We are comparing in this slide the cost of or the speed up from calculated from computing these operations using the CSR format. And now we did a simulation where we removed all the cost of indexing, so we are not accounting for the cost of indexing, and observe what is the potential speed up that we could achieve. It's pretty high, it's more than 2 times that we could achieve by implementing an ideal indexing mechanism that was essentially for free. So this is a very good motivation for trying to reduce the cost of indexing in sparse matrix operations. So let's try to come up with a new compression format. We need the compression format to be general, but the problem with general compression formats is that they are optimized for storage. So it's difficult to find the non-zero elements. It's the indexing overhead that we mentioned in the previous slide. There are also some specialized formats where it might be easier to find the non-zero elements because there is an assumption about a specific matrix characteristics. These formats are specialized, for example, for diagonals, but the problem with them is that they have narrow applicability. So the question here is, what is an ideal compression format? We want to have a sparse matrix compression mechanism that minimizes the indexing overheads, as we have discussed. It can be used across a wide range of sparse matrices and sparse matrix operations, and also that enables high compression ratio. We want it to be space efficient. So in order to do so, what we did was proposing this SMASH compression format that is a bitmap-based compression format. So the key idea in SMASH is to provide a hardware-software cooperative mechanism that enables highly efficient sparse matrix compression and computation, and is general across sparse matrices and sparse matrix operations. SMASH is based on software side, that is the efficient compression using a hierarchy of bitmaps that we are going to discuss, and the hardware unit that scans the bitmaps to accelerate indexing. In between, we provide an ISA, some instructions to control the hardware from the software. We are going to focus on the software compression scheme because it's also applicable to our own software developments. For details related to the hardware and the architecture, the ISA of SMASH, I would recommend you to take a look at the paper that it's in a later slide. The link to the paper is in a later slide. So let's focus on the software side. The compression scheme, the proposed compression scheme encodes the positions of non-zero elements using bits to maintain low storage overhead. So in this bitmap, we are going to encode a block of the matrix that contains at least one non-zero element. And also, if this is our matrix on the left, and these are blocks of a certain number of non-zero elements, if there is a certain number of elements, if there is one non-zero element, this one non-zero element in this block here, we will mark the corresponding bit of the bitmap as 1. So here we do the same for the remaining 0 blocks where we don't have non-zero elements. The bitmap will contain a 0. So the problem with this bitmap is that it might itself be pretty large because it might contain a high number of 0 bits. So the idea here is to apply the same encoding recursively on the bitmap in order to compress more effectively. So by doing so, we come up with a hierarchy of bitmaps. Observe how we first compress the matrix itself using the non-zero values array, and then the first level, the bitmap 0, that points to the array of non-zero values. Then we can compress the bitmap by, for example, compressing blocks of bits. In this case, 4 are compressed as this one because at least one of these bits is equal 1. However, for the next chunk of 4 bits of the bitmap 0, this is 0 because there are no non-zero bits. So that's why we encode it as a 0. And then we can continue to the next level of the hierarchy, in this case, bitmap 2. So now, observe that we are applying different compression ratios, and this is something that is also configurable, and depending on the specific characteristics of the matrix, it might make sense to use different compression ratios. But yeah, in this particular case, we have used a compression ratio 4:1 from bitmap 0 to bitmap 1, and 2:1 from bitmap 1 to bitmap 2. So now when it comes to finding one element, a specific element in the array of non-zero values, we have to go through the bitmaps starting from the highest level of the hierarchy, bitmap 2, then go to bitmap 1, from there to bitmap 0, and from there to the array of non-zero values. So this hierarchy of bitmaps is efficient in terms of storage, is fast to be indexed, and is also hardware friendly. And here you can see some results, the performance improvement that we achieved using SMASH, the hardware software co-design proposal for different workloads like SPMB, SPMM, and PageRank and VC that are respectively based on SPMB and SPMM. We compare here to the TACO library with 2 different formats, CSR and the block CSR format. We normalize the results here to the TACO CSR format, and these are the results for the block CSR format, and these are the results for SMASH. As we can see, SMASH provides significant performance improvement over the state-of-the-art formats. And as I said, SMASH can also be applied software only without having the hardware extensions that we propose in the paper, and this software only version of SMASH outperforms TACO CSR. We evaluated different matrices with different levels of sparsity, and evaluated was the storage efficiency of SMASH compared to CSR. We can see that for very, very low or very, very high sparsity, very, very few non-zero elements that are these matrices here. CSR is slightly more efficient in terms of compression, but for the majority of matrices that we evaluated, SMASH is more space efficient than CSR. And here you can find the link to the paper. So now let's continue trying to improve SPMB and other operations with sparse matrices. And remember that one of the key architectural innovations in the recent architectures of NVIDIA GPUs was the inclusion of these tensor core units that are specialized for machine learning and can provide amazing throughput for deep learning, amazing throughput in terms of multiply and accumulate operations. This is the core of the NVIDIA A100. In every architecture generation, NVIDIA keeps improving the hardware. In the recently announced H100 architecture, they keep improving the tensor cores. This is fourth generation of the tensor cores, including new floating point formats. And one question here is, okay, so these tensor core units were originally designed to work on dense matrices, operate with dense matrices, but is it possible to use them to operate on sparse matrices as well? Well, that's something that we proposed a couple of years ago, and yet I think it's really worth taking a look at this work as well. Before we go into the detail, let me remind you what are the tensor core units. Tensor core units are specialized processing engines, processing elements that we find in each GPU core of NVIDIA GPUs, where they perform matrix multiplication on small tiles, on small matrices, for example, of size 16 by 16. They use typically mixed precision. The operands are, for example, represented in a floating point 16 bits, while the results, the accumulators use 32-bit floating point. And this is essentially the computation that they perform, the multiplication of two submatrices or two small matrices or tiles of two matrices, A and B, and then we can also add a different matrix C. We can do a multiply accumulate operation or a multiply add operation, as you can see. We introduced tensor core units in previous lectures, and we even gave a short introduction about how to program them. You can watch that in our lecture 8. So now let's start talking about T-sparse. That is this proposal to use the tensor cores for computation with sparse matrices. Remember that we have discussed in this lecture different compression formats, like, for example, the COO compression format. Remember that in the COO compression format, for each non-zero element, what we are doing is storing a row index, column index, and the non-zero values. We have also discussed compression format that uses a bitmap. Remember that in the SMASH compression format, what we do is compressing non-zero blocks. We will store these non-zero blocks that are blocks or chunks of the matrix that contain at least one non-zero element, and we create a bitmap for them, and we can even create a hierarchy of bitmaps. And here in this T-sparse work, we are proposing the use and a different bitmap-based format. It's different in the sense that what we are doing is not using the bitmap to mark whether a chunk of the matrix contains non-zero elements or not, but inside each of the chunks of the matrix or inside each of the tiles of the matrix, we define what are the elements that are non-zero by creating one bitmap per tile. And that's what we do here. This is our input matrix. Observe that we divide this input matrix into 4 tiles, 0, 1, 2, and 3. And then for each of the tiles, we create a bitmap based on the elements of this tile that are non-zero. So it's because first element is 0, this first bit here is 0, next element is 1, this bit here is 1, This element here is also non-zero, so this next bit is 1, and the last element is a 0, so the last bit of the bitmap is 0 as well. So we have one binary number for each tile. Each bit is set to 1 if there is an element that is a non-zero value in the corresponding position. And then we also have to, we also have the array of non-zero values that we need, of course, and we will also need to store, we will need to keep the coordinates of the tiles in the dense matrix. So this is the tile 0, 0, this is the tile 0, 1, this is tile 1, 0, and this is tile 1, 1. And now, how do we load the sparse bitmaps into the TCUs? We are going to make use of the TCUs, but not the complete TCU. For example, assuming that we are using the default configuration of 16 by 16 tiles, what we are going to do is mapping 2 tiles of 8 by 8 on these 16 by 16 tiles that the TCUs provide. We cannot use all functional units or processing elements here. We will have, because otherwise we won't obtain correct results. But still, you're going to see that we are going to get good performance improvement thanks to the use of the tensor core units. Another important question, because this is a sparse matrix computation, is that we need to allocate memory for the output, and how many elements do we need to allocate? Because unless we have a clear understanding of the matrix and the vector before performing the operation, well, in this case is matrix multiplication. In this sparse work, we don't know exactly how many non-zero elements we are going to have in the output, and there are different ways of handling this, as it has been done by previous works. One possible solution is to allocate an upper bound of the amount of memory that we need, or use some probabilistic estimation, or maybe perform a precise count of what are the output elements, that non-zero elements that we are going to use, etc. And in this work, we use a precise method. In order to do so, what we first use is counting kernel. This counting kernel is kind of a simplified matrix multiplication where we are only using the values, the bitmaps, and based on that, we count how many non-zero elements we are going to have in the output matrix, and based on that, we will allocate as much as we need. But more interesting is to see how we find the tiles that we have to multiply. In order to perform the multiplication and schedule the multiplication of tiles or submatrices onto the tensor core units, what we create is a task list based on the tiles that we will have to multiply. So for example, in order to calculate the tiles of this output matrix C, notice that we are using this input matrix A, input matrix B. They have tiles with non-zero values. For example, these 1 here, these 4 here. So we can match those tiles. We can first match those tiles that we will have to multiply. In this case, these tile 1 from A, tile 1 from B, and we put them together in our task list. Then we go to tile 4 in A, tile 4 in B, and we put them together in our task list. And then we continue doing the same for the rest of tiles that we will have to multiply. So we first find which tiles of A we need to multiply with tiles of B in order to obtain tiles of C. And then we group intermediate products using a segmented sort algorithm. So observe that all these tiles that we put first are going to contribute to this tile. These multiplications of tiles are going to contribute to this tile C0. Then we have tile C1, C2, C3, etc. And then we are going to feed the tensor core units by using this list of tasks. So and this is how we could map this particular example to compute C0, to compute C1. What we are doing, observe, is mapping A1 and B1 in the same location, in the same part of the 16 by 16 tile. Remember that here we are, the effective part that we use from the 16 by 16 tiles are these two subtiles of 8 by 8, where we place here A1, B1, and here A3, B3. Observe that they correspond to different output tiles. In the second iteration, we map the second pair of tiles from A and B, in this case A4 and B4, and we accumulate because they are in the same part of the output tile, as we can see in this part here. So the accumulated result of A1 times B1 plus A4 times B4 gives us Z0, and we calculate C1, essentially doing the same thing for the corresponding tasks and the corresponding tiles. After that, we need to obtain the bitmap of the output matrix C, and in order to do so, what we make use of is this valid function, this warp wide valid function. Each thread of the war will check whether the corresponding element is 0 or not, and based on that, we create the bitmap. Now, how does this T-sparse proposal compares to the state of the art? As you can see here, so here we are showing a speed up of T-sparse over the state-of-the-art methods such as Q-sparse, CUSP, merge, R-merge to N-sparse, and also compared to the own T-sparse method without using the tensor core units. And we see that in all cases, we obtain speed up in terms of geomean. Now, it's not a perfect solution for all different matrices, as you can see, but the average results are pretty positive. And the TCUs themselves, using the TCUs for this calculation is definitely effective, as we are obtaining 82% more performance than the version that doesn't use the tensor core units. And also, as you can imagine as well, we observe that T-sparse works better with denser tiles. And this definitely makes sense, because the more dense a tile is, the more use we are doing of the processing elements in the tensor core units. And if you want to learn more about this method, I would recommend you to check our paper, and also you can access the code in or the public repository. And one last important thing to say about sparse matrix computation, and in particular about SPMB, is that these operations are typically memory bound due to the way that we have to access memory. We have to access memory pretty frequently due to the way that the matrices are compressed. And in the end, there is not so much computation, because the matrix vector multiplication is essentially one multiplication and one addition per input element of the matrix for the non-zero elements of the matrix. So if we analyze the characteristics of the kernel and we perform a workload characterization, for example, using the popular roofline model, we will observe that SPMB falls here in this memory bound area of the roofline, because its operational intensity is relatively low. As I said, just one multiplication and one addition every element of the matrix and the vector that we use. So that causes that SPMB falls under the the performance roof imposed by the memory bandwidth. And for these kind of workloads that are in the end limited by the access to data, we are observing more and more proposals that relate to processing in memory. Processing in memory is a paradigm that proposes to place some sort of compute capability near in memory or inside the memory in order to accelerate those workloads that require lower memory access latency and larger memory bandwidth. This is a toy representation of a typical processing in memory system, similar to the ones that we can already find in the market. Observe that the host CPU is connected to some DIMMs of DRAM that are still working as the main memory, but then also connected to the memory channels and the memory bus. We have some DIMMs of PIM-enabled memory, where we find DRAM banks, but we also find some processing elements that we call here PIM cores. And these processing in memory systems are nothing futuristic. They already exist. This ABMEM architecture is coming from a French startup, is already commercial, and hopefully we will also have soon other PIM systems coming from major DRAM vendors such as Samsung or SK Hynix, as they have announced in recent times. So by using one of these systems, in particular the ABMEM PIM system, what we did is developing a library for SPMB with many different combinations of matrix formats, data types, and optimizations. In total, we developed 25 SPMB kernels, and we perform a comprehensive analysis of all these kernels using different input matrices. We applied many different optimizations, for example, in terms of how to partition the computation across the available PIM cores. We explore, for example, 1D partitioning, where we perform the complete computation on the PIM cores, and also the 2D partitioning, where we have to, because the rows are partitioned, as you see, across different cores. So we have to perform the final reduction on the host side, but here we trade off computation versus data transfer costs. This Sparse P is publicly available. You can access the code. This is a list of all the different versions that we implemented with different sparse matrix formats, different load balancing and synchronization mechanisms, and different data types. And if you want to learn more about this implementation of SPMB using processing in memory systems, I will definitely recommend you the lecture that we are delivering this Thursday. It's delivered by Cristina Gianola, who is the first author of the SPMB on processing in memory work, and I'm pretty sure that it's going to be a very interesting talk that will give you few more interesting, important hints on how to optimize such important kernel, SPMB, and also other computations involving matrix, sparse matrices. If you want to read the paper, you can access it. It's publicly available in archive already, and the repository as well. You can access all codes or 25 versions in all repository. So I hope you found this lecture interesting. I think it's definitely a challenging a parallel pattern. Everything involving every operation involving sparse matrices is going to be challenging to implement, but also extremely exciting to do it on parallel processors like GPUs. If you want to learn more about this topic, please read chapter 10 of the book Programming Massively Parallel Processors. So this is all for today. Thank you very much for your attention, and please feel free to reach out to me if you have any questions or want to discuss anything related to this lecture or the course.